Hi, everyone. This week, we're going to start the chapter on simple linear regression. Our goal for this week is to cover how to set up the data and how to understand whether or not it's appropriate to interpret simple linear regression results. Next week, we'll focus on interpreting the results, assuming that all assumptions are met. A simple linear regression is a method of testing a relationship between two continuous variables to identify whether or not those variables are trending together in a particular way. Now, if you think back to earlier in the semester, we studied correlation, and we defined it in essentially the exact same way. So what's the difference? Well, mathematically, there's very little difference. And in fact, you'll see just how similar they are next week. With the simple linear regression, we make an assumption that one of the variables is causing a change in the other, that one of the variables is independent and the other is dependent on that independent variable. With the correlation, we make no assumptions about causality. You may have heard before in your classes that there is a very strong correlation between ice cream sales and violent murder. As ice cream sales go up, so too does the rate of violent murder. Although those two variables are strongly correlated, one does not cause the other. They are both caused by increase in heat. As the weather goes up, so do ice cream sales and irritability. If we wanted to look at those variables in terms of correlation or simple linear regression, we would correlate the ice cream sales and the violent murder, but we could look at simple linear regressions from temperature change to violent murder or from temperature change to ice cream sales. Think back to your algebra class. Our output from a simple linear regression is going to look very similar to the equations you plotted on a graph whenever you were in algebra. Do you remember y equals mx plus b? Well, that's practically a simple linear regression equation, but we'll talk about that more next week. For now, it's important that you just understand that regression output comes in the form of equations that can be plotted. If you create a scatter plot of your data, and the data appears to be trending on a line that looks a bit like this, pretty straight, and projecting upward, we say that you have a linear trend. In fact, a positive linear trend, because as your x values increase, your y values also increase. X will represent your independent variable, and y will represent your dependent variable. Linear trends may also look like this, such that as your x variable increases, your y variable decreases. Another possibility is that your line is curvilinear, that the increase or decrease is not constant. Think back to when you graphed a parabola in your algebra class. Similar trends can be seen in regressions. Regressions can also take a shape that looks sort of like an S, and this would be a logistic shape. I don't see this in a lot of business data, but we certainly see it in a lot of testing data, such as the data that identifies whether a certain problem on the SAT or the GRE is working well. Regressions can also take an exponential curve type shape. The shape of your regression line is always revealed through a scatter plot. Before you interpret data from regression analysis, you need to be sure that the four assumptions of a regression analysis are met. The first is that the relationship between the data are linear. We can tell pretty well whether this assumption of linearity is met just by looking at a scatter plot. Second, we assume that all of the errors in your data are independent from one another. Now, error deals with things that keeping an individual data point from being exactly on a predicted trend line. We need to assume that all errors are independent, that there's not something within the data that is systematically causing error across all of your data points. In business, the only time that we really see this violated is with time data, if we're looking at data that happens over a course of time. When we find that we don't have independent error, that the same thing is causing error over and over and over again, Then we have to use a non-parametric statistic in order to test our data. The third assumption is that our errors are normally distributed. As we've discussed before, unless there is a systematic problem with our data, then the errors should not all be clustering to one side of the mean. And the last assumption is a word that I pronounce incorrectly more than any other in my lexicon, and that word is homoscedasticity. And that's probably the only time you're going to hear me say that without a struggle in this lecture. Essentially, homoscedasticity means equal variance, that if we plot our regression line in a scatter plot, that about half of our data points should be above that regression line and about half the points should be below the regression line. Let's look at some data to make this less abstract. This data set profiles the average socioeconomic status of customers across 14 different stores and compares that to the sales at those stores. Customer profiles are rated on a scale of 1 to 6, and sales are rated on a scale of 1 to 12. We can run a linear regression on this data, assuming that the socioeconomic status of the customers, on average, will predict the sales of that store annually. To do that in Excel, we pull up our tool pack. We go down to linear regression for our Y range. And it's very, very important that we know which of our data represent Y and which is X. For our Y range, we want our dependent variable, the variable that we think is affected by the other variable. So for our Y range, I'm going to choose annual sales. And for our X range, I'm going to choose the profile of the customers. I'm not going to assume that the constant is 0. This means making the assumptions that when you plot your regression line, that the y-intercept will be 0. There's no need to assume this. I'm going to tell it start outputting the data in E1, and I'm going to tell it that I want all of the options. And when I do that, I get a lot of output. Let's start by looking at our scatter plots. This scatter plot profile customers residual plot. It plots the residuals by the profile customers, which means our residuals by our independent data. Residuals are our error. So when we talked about normality of error, we were talking about normality of residuals. When we talked about independence of error, we talked about independence of residuals. If we meet the assumption of normality of error, then we should see that our data are split fairly equally around 0. And here, that's what we see. So we're not worried that we violated the assumption of normality of the error. Our next scatter plot is something that earlier this semester we called a colored scatter plot. It's a scatter plot such that the different colored dots represent different data. The red dots represent the actual annual sales. The blue dots represent the predicted annual sale. So again, with regression, we are trying to output an equation that exactly predicts where our data would fall. See how these blue dots fall on a perfectly straight line? That's because they represent the data as perfectly predicted, whereas the red dots are what we actually observed. The red dots aren't so perfect. They're not ideally aligned, and that's okay. We don't expect them to be. What we do expect is that we're going to see some clustering in those red dots rather than the red dots being spread all over this axis. So what we're seeing here is that, yeah, we've got a couple of outliers, but overall, our data appear to be trending pretty linearly. So we're not worried about violating the assumption of linearity. Our third plot is something that you've seen before. It's a normal probability plot. This doesn't tell us about whether we violate any of our assumptions, but it does tell us that, yeah, our data is fairly normally distributed. Now let's look at some of our output. Let me expand these columns so that it's easier to read. This is going to be a lot of where we focus our attention next week. The multiple R and the R squared in particular. Here is where our actual equation comes from. According to our regression equation, Y, our dependent variable, which is annual sales, is equal to negative 1.209, we'll say, this intercept, plus our beta coefficient, which we'll call 2.074, times our independent variable. So what this means is that according to our simple linear regression, for any customer profile value that we put in here, multiply by 2.074, and add a negative 1.209, we should get a rough estimate of the annual sales of the store. This equation right here is where these blue dots came from. Here in the residual output, we have our residuals, which is how far each data point fell from where it was supposed to fall in our dependent variable. And then we have the standardized residual. Standardized residuals are calculated by taking the residual score, subtracting the mean of the residuals, and then dividing by the standard deviation of the residuals. This essentially turns your residual errors into z-scores. So we would find outliers in z-scores by looking for standard residuals that are less than negative 1.96 or greater than positive 1.96. And we see that we only have one residual that is concerningly high. So all but one of our data points look like really good predictors. If we take the average of these standardized residuals, that output should be really close to zero. And here we find that this is tiny. Remember, this scientific notation says that the real number is what you get if you move this decimal point 14 places to the left. As long as that mean of the standardized residuals is close to zero, which this is really close to zero, then we're not worried that we violated assumptions of muscodasticity. So that means that the last assumption that we need to check for is the independence of error. This is something that you do with what's called a Durbin-Watson test. And again, it's not something that we typically worry about in business unless we have time series data, but it's always good to check for it. Unfortunately, we don't have a quick way to do this. So we've got to do some math. And it all has to do with these residuals. So I'm going to copy these so that I can do some manipulations with them. The Durbin-Watson equation is sum of squared difference of residuals divided by sum of squared residuals. Then you get a ratio that you're hoping is close to 4 and far away from 0 that will tell you whether or not you violated this assumption. So the first thing we need to do is calculate our sum of squared residuals, which means all of these values squared and then we calculate the sum of the squared difference of residuals. This is a weird one, I'm not going to lie. You take your residuals and then you stagger them by 1. And then for every row that still has two values, you take the difference. Then you square those values. And then we'll take the sum of the squared difference of these residuals. Then for our Durbin-Watson, we take this value. So back here, our Watson-Durbin, that is equal to this value divided by this value. So again, for our Durbin-Watson, be scored on a range of 0 to 4. And if you look in your textbook, there's a very specific set of values that tells you exactly what the range of ideal versus slightly concerning versus unacceptable scores are based on your sample size. But a general rule of thumb is if it's over 3, you're safe. You're very, very safe. So with that 3, we know that we do not violate the assumption of independence of errors. Now, I'm also going to show you how to look for these things in SPSS. Here again, I've loaded our data. We have a column for store, profile, and sales. I've told SPSS that even though store is numeric data, it's nominal because each of those numbers just represent a different store. Whereas our profile of customers and our sales data are scale data. Here's what it looks like in the data view. To analyze in SPSS, you go to Analyze, Regression, Linear. I'm going to tell it that as my independent variable, I want to use the profile data. For my dependent variable, I want to look at sales. I can also tell it that I want plots. I would like a normal probability plot, and I would also like for it to plot the observed and predicted values of that dependent variable. Additionally, if I go into statistics, I just have to click a box to tell it that I want it to do the Durbin-Watson analysis. So if I hit continue and OK, here's that output. You see that our y-intercept and our beta are the same. You also see that we have that normality evidence and equal variance. And if I go back up to the model summary, there is that Durbin-Watson test given to us very simply without having to do any of the extra work that we did in Excel. So this is your introduction to simple linear regression all the way up to testing the assumptions of regression. Please let me know if you have any questions.